Particle physicists in the United States have tried to come up with a strategy to revitalize their research area, and their ideas are somewhat underwhelming. But let's have a look. Last week, a panel of scientists named the Particle Physics Project Prioritization Panel, or P5, signed onto a list of policy recommendations for the US Department of Energy and the National Science Foundation. And since 5 is such a nice number, they've come up with 5 priorities. Their highest priority after continued funding for already running projects is, interestingly enough, not a particle physics project. It's a radio telescope array called CMB-S4, whose detectors would be distributed in Chile and Antarctica and possibly some other places. CMB stands for Cosmic Microwave Background, and S4 means it's the 4th stage of an already existing project in stage 2. The major purpose of this experiment would be to measure the polarization of the cosmic microwave background. The microwave background is the radiation that's left over from the hot plasma that was around in the early phases of the universe. The polarization of this radiation gives you an orientation for each patch of the sky. This orientation is partly caused by dust in the Milky Way, but partly it comes from fluctuations of space-time in the early universe. It's this signal from the space-time fluctuations that physicists are after. If you remember, this CMB polarization is what the BICEP experiment claimed to have found in 2014. But their detection turned out to be dust in the Milky Way, which prompted my friend and YouTube neighbor Brian Keating to write a book called Losing the Nobel Prize. They want to measure the imprint of these space-time fluctuations because, you see, their prediction of the most popular but unconfirmed theory about the beginning of the universe, inflation. The idea of inflation is that our universe was born out of quantum fluctuations of a field called the inflaton field. It supposedly caused a rapid expansion of the universe, so the universe inflates, thus the name. The inflaton later decays into normal matter, which is convenient because then it isn't around today to be detected. But the quantum fluctuations of the inflaton field should also cause fluctuations of space-time, and this should cause the polarization in the CMB that they're looking for. The devil is, as usual, in the details. The issue is that there are other ways to create these space-time fluctuations and the polarization that comes with them. It doesn't have to be inflation. And the other way around, there are some models for inflation in which the effect would be so small one wouldn't see it. So even if they can measure this signal, it'd neither confirm nor falsify inflation. It's also somewhat surprising that particle physicists go for what's a cosmology experiment, but rumors say it's because the Astro budget wouldn't completely fund the experiment, so they're helping out their friends, basically. But friends don't let friends look for inflatons. Okay, that was the top priority. Then let's look at the second one. The second one is an upgrade of the DUNE experiment. DUNE is the deep underground neutrino experiment currently under construction at Fermilab. Its task is to shoot a beam of neutrinos through Earth's crust to Sanford Lab in South Dakota, about 1,300 kilometers away. With that, particle physicists want to learn more about neutrinos, especially their role in CP violation. Some particle physicists think the CP violation is necessary to explain why there's more matter than antimatter in the universe. There's no reason it should have been the same amount, other than that particle physicists think that's what nature should have done. So I think there's nothing to explain and it's a pseudo problem. But then I wasn't asked for an opinion. I wonder why. But why would they give so high priority to upgrading a project that hasn't even yet been completed? It's because DUNE has become a major headache for Fermilab. The management has been miserable and the cost has spiraled out of control. DUNE was originally proposed with a cost projection of about $1 billion, but it kept getting more expensive. The Department of Energy put a cap on $3.1 billion. I have a lot of sympathy for that. If someone was spending my money at $3.1 billion, I'd also get a little antsy. Fermilab got a new director, a bad grade from the DOE, and is about to get a new management. That budget cap, however, means that the project would have to be shrunk so much it wouldn't be able to measure the CP violation before 2035 or so. So what particle physicists say is that they want the project to be built as originally planned, despite the ballooning cost, because otherwise chances are that some other country manages to do it first, which, from the point of view of international competitiveness, would blow the entire money into the wind. This makes me think that the likely reason for making this a priority is the sunk cost fallacy, also known as throwing good money after bad. The third priority is to support the international efforts to build a huge particle collider that would produce a lot of Higgs bosons to further study them. They didn't put a new US-based collider among the top priorities, but they have them in a later recommendation. They want to build a muon collider in a project they call the Muon Shot, a pun on Moonshot, the title of a book about the American Apollo program that brought the first people to the moon. Muons are elementary particles in the standard model of particle physics. That they're elementary gives a muon collider a big advantage over hadron colliders like the LHC. That's because hadrons, like the protons that the LHC accelerates and collides, are composite particles. If you collide them, you divide up the entire energy into collisions between the constituents. It's not very efficient. In a muon collider, you get more of the energy from the particles directly into the collision. So a muon collider of 10 TeV could do much more than the LHC already. So this is what the Muon Shot is all about, but at the moment they're just saying they need to make plans and the project itself is not a priority. So let's get back to the priority list. The fourth item is a dark matter direct detection experiment reaching the neutrino fog and preferably sited in the US. Dark matter is one of the explanations for some astrophysical observations, such as the two fast rotations of galaxies. Particle physicists like the idea that these observations can be explained by a new type of particle called dark matter, if that exists, which it may not. The trouble is, no experiment has found those particles, and each time an experiment comes back empty-handed, they say the particle is a little more weakly interacting, like this xenon NT experiment that was upgraded from xenon 10 to xenon 100 to xenon 1T and now to xenon NT without finding anything. For a long time, particle physicists said there'd be an end to this building of ever larger detectors, because eventually the hypothetical particle would have to be more weakly interacting than neutrinos. So the neutrinos then create so much noise that you can't find the dark matter particle. This is what's called the neutrino fog. But some others pointed out this just means you need to figure out how to subtract the neutrino noise so you can find the supposed dark matter signal in the data. This new experiment, which they want to build, would be reaching this neutrino fog. Of course, there's still no reason to think that there's actually a new particle to find there, so I continue to be unimpressed. Let's then look at the fifth and final priority. That's an upgrade of IceCube, which is a detector at the South Pole. The detectors are actually sunk down into boreholes into the ice. It's amazingly cool in any sort of interpretation of the word, because there's very little noise down there. IceCube can tell us more about neutrinos and dark matter particles, if they exist, which they may not. In summary, this plan of particle physicists is basically more of the same stuff that hasn't worked in the past 4 decades. Personally, I think what they should do is spend some money on serious theory development and then come up with some well-motivated experimental proposals rather than wasting more money. But then again, it's not my taxes which are being spent on it. Mine apparently subsidize coal. I might be warming up to those dark matter detectors. Scientists have long speculated that life didn't begin on Earth, but in space. According to a new preprint, life could have come from intergalactic gas clouds. So let's have a look. The oldest confirmed traces of life are biostructures called stromatolites. That's layers of rock which contain remains of single-celled organisms. These organisms are believed to have been either algae or some kind of bacteria. Scientists have dated them back to about 3.5 billion years. Earth itself is about 4.54 billion years old, but when it formed, it was really hot and had no solid crust. Life back then wasn't possible, but at the young age of about 500 million years, Earth had cooled enough for the surface to become partly solid. There were still frequent volcano eruptions, but most scientists believe that life emerged after the surface temperature had dropped below the temperature where water boils. Back then, the Earth's atmosphere was very different from what it is today, with high levels of carbon dioxide and nitrogen, water vapor, and toxic gases that were released during volcanic activity. There was also still a lot of stuff flying around in the solar system, so there were frequent meteorite impacts. Basically, a toxic atmosphere with frequent microaggressions. Going by the available evidence, scientists place the origin of life between roughly 3.9 and 3.7 billion years in the past. But just how life began on Earth is one of the big unsolved problems of science. Somehow, all this inert matter must have combined to self-replicating molecules that could adapt to their environment and, after some billions of years, achieve this pinnacle of evolution, YouTube. But just how did that happen? No one knows. The first idea was that lightning strikes did it, going back to a now famous experiment by Stanley Miller and Harold Urey in 1952. They created a closed system from 2 glass flasks and filled that with gases that they thought mimicked the early Earth's atmosphere. Then they added electric sparks to simulate lightning, which they believed to have been common on early Earth. A week later, they found that their flask contained several amino acids, the building blocks of proteins. That got everyone very excited, and for a brief and glorious time, scientists thought the problem had been solved. But then other researchers pointed out that the atmosphere on Earth back then would have been different, so it couldn't really have worked like this. Then again, others said maybe we're misinterpreting some of the data, or it worked differently, maybe life emerged near underwater volcanoes or in hydrothermal vents, or some vital ingredients came from meteorites, and so on. If you think all of this sounds a little crazy, I won't blame you, but there's actually evidence to back up at least some of it. Scientists have indeed found life on Earth in some of the most unexpected places, from hydrothermal vents at the bottom of the ocean to the glaciers of Antarctica. Life, it seems, is unexpectedly robust and can survive in incredibly difficult circumstances. They've also found the building blocks of life, amino acids, inside of meteorites and even in outer space. And this brings us to the idea that the first life on our planet arrived fully formed from outer space. It's known as panspermia and says that life originated elsewhere, either on another planet or indeed in outer space, rained down on Earth from meteorites or dust, and found Earth to be a welcoming environment. Some even go so far to say that life was deliberately seeded by aliens to spread through the universe. And that brings us to the new paper. In the new preprint, a researcher from China looked at the possibility that life on Earth came from molecular clouds in space. Molecular clouds are dense clouds of gas and dust in interstellar space where new stars form, and God knows what else. These clouds are believed to be mostly made of hydrogen, but we know from spectral analyses that many other chemical elements can form there too. That makes these clouds good candidates for spaceborne life. The author says that these molecular clouds could sustain life in the form of methanogenic bacteria. They are called that way because they generate methane. Some of the first forms of life on Earth have indeed been of this type. Furthermore, it's so cold in these clouds that the hydrogen is liquid. This means it could be contained by cell membranes, and the microbes could use it to transport molecules through the membranes. The author also says there is enough carbon monoxide, carbon dioxide, and hydrogen in the clouds to keep the bacteria alive. The paper does not explain, however, how this life came about in the first place, just that some forms of life could have survived in those molecular clouds. That sounds possible, but is it right? Well, more research is needed. Personally, I like the idea that where's someone's bioexperiment gone badly wrong? Physicists at the University of Warwick in the UK are starting to build an experiment that could just save physics. Let's have a look. Research in the foundations of physics has been stuck for about 40 years, ever since the development of the Standard Model was completed. The big questions that were open then are still open today. What's dark matter? How does a measurement work? And how does gravity work together with quantum physics? Physicists have tried very hard to answer these questions, but nothing's come out of it. This new experiment is taking on the latter question. How does Einstein's theory of general relativity work together with quantum physics? The problem is that mathematically the two don't want to cooperate. We just talked about a possible solution to this problem last week. This new solution has it that gravity doesn't become a quantum theory, but instead has random fluctuations. But most physicists don't think this is how it works. Most physicists think that gravity too is a quantum theory. And since Einstein taught us that gravity is really caused by the curvature of space-time, this means that space-time itself must have quantum properties. So we have these two possibilities. Space-time gets quantum properties, and with that gravity does too, or it doesn't. How could you find out? For a long time, physicists thought it's just impossible to test this because the effects of quantum gravity are just too small to be measurable. I've spent 10 years trying to argue against that, but eventually gave up because I couldn't get funding for it, but that's another story. Be that as it may, I'm very excited to see that finally some experiments are underway, and Glitter Albert agrees. This new experiment in Warwick rests on a very simple idea. Entanglement is a type of correlation between two objects that is specific to quantum mechanics. To create entanglement between two quantum objects, the mediator that creates the entanglement must also be quantum. So the idea of the experiment is to take two small diamonds, make sure that gravity is the only force between them, and then measure whether they became entangled. If they did become entangled, gravity must be a quantum force. The idea for this experiment has been around for some time. It's a good idea in principle, but in practice I think it'll basically be impossible to eliminate the possibility that something else created the entanglement. You see, most people think of entanglement as something very special, but rather the opposite is the case. Everything gets constantly entangled with everything else around you. That's because all those atoms bounce off each other and so on. Indeed, the press release contains a very nice quote from David Moore. We need to eliminate all interactions between the nanoparticles other than gravity, which is incredibly challenging since gravity is so weak. The problem is the following. The most likely thing this experiment will find is that these two diamonds do get entangled. Then they'll have a hard time to argue it must have been gravity and nothing else. If the diamonds don't get entangled, even though gravity acts between them, then that could be used to rule out the possibility that gravity was quantum. But this seems extremely unlikely to me, both because I don't think that it's possible to measure and because I don't think that gravity is non-quantum. I'm therefore more enthusiastic about another experiment that's logically kind of the opposite. This is an experiment which the group of Markus Aspelmeier in Vienna is working on. They want to bring two small masses into a superposition of two places and then measure where the gravitational pull goes. Depending on whether it's quantum or not, it should go to the middle or fluctuate between the sides. Now the thing is that in this kind of experiment, if you manage to keep the noise down, it'll show you that gravity is quantum. With the other experiment, it's the opposite. So this is why I'm more in favor of the Aspelmeier experiment, though I think both should be done. If you didn't really understand that, don't worry. I've been saying this for 10 years and no one understands it. I'm just recording this so that when they do their experiment in Warwick and the result is inconclusive, I can put on a smug grin and say, "See, I told you so." I thought I have a talent for pissing off climate scientists, but I have to bow to Sultan Al-Jaber, who had climate scientists fuming for saying that there's no science behind a fossil fuel phase-out. He is, of course, entirely correct, which raises the interesting question whether fuming climate scientists emit carbon dioxide and if we need to phase that out. But first, some background. Sultan Ahmed Al-Jaber is the Minister of Industry and Advanced Technology of the United Arab Emirates. The UAE are the world's sixth largest producer of petroleum after the United States and Canada. Yes, that's right, they actually produce less than either of our friends in North America. It's just that they're less good at keeping quiet about it. Al Jaber is also head of the Abu Dhabi National Oil Company and was head of the COP28 climate meeting, which took place 2 weeks ago. The COP28 meeting was rather foreseeably a waste of time, but let's listen to what the man said that upset climate scientists so much.
And there is no science out there, or no scenario out there, that says that the phase out of fossil fuel is what's going to achieve 1.5. 1.5 is my North Star. And a phase down and a phase out of fossil fuel, in my view, is inevitable. It is essential, but we need to be real, serious, and pragmatic about it.
To me, that sounds perfectly reasonable. Science tells us that the reason for global warming is the increase of carbon dioxide in the atmosphere, caused primarily by our continued burning of fossil fuels. It doesn't tell us that we need to do anything about it. And if we do anything, it doesn't have to be phasing out fossil fuels. That might be the smart thing to do, but there's no law of nature that says humans need to be smart, is there? Indeed, it seems very likely to me that we'll decide on a stupid way to handle the situation, which is to continue pumping carbon dioxide into the atmosphere and then try to get it back out. This is called carbon dioxide removal, CDR for short, and it makes about as much sense as letting the dog pee into the pool because, well, you can filter it out, right? One type of carbon dioxide removal is direct air capture, which works by pushing air through filters, extracting the carbon and burying it underground. It's not much of a secret that the oil industry hopes they can use some sort of carbon dioxide removal to offset their emissions, not including the emissions caused by burning their products, which really isn't their fault, is it? Indeed, the oil company that Al Jaber is head of launched a new carbon capture plant just a few days before the COP meeting. The target for the plant is 1 ton of carbon dioxide a day. Just for context, at the moment we emit globally about 55 billion tons of carbon dioxide per year. But it's not just oil companies who have taken a liking to carbon dioxide removal. The US Department of Energy funds several of these projects. For example, this one, which is a collaboration between Lehigh University in Pennsylvania and the company Advanced Cooling Technologies. They want to extract energy for the process from geothermal sources. These projects are now popping up all over the world. Of all the stupid ways to remove carbon dioxide from the atmosphere, direct air capture is quite possibly the stupidest. It makes considerably more sense to prevent the carbon from getting into the air to begin with, which is called carbon capture and storage. This can reduce carbon emissions from fossil fuels, but you can also do it when you're burning trees or other vegetation. In this case, you have basically used the trees to filter the carbon dioxide out of the air, and then you can store it underground. This is called bioenergy with carbon capture and storage, and has the added benefit that it also generates energy. The issue is now, as I explained in our recent video on net zero, that all remaining plans to get to net zero by 2050 rely on carbon dioxide removal. This will give fossil fuel companies an excuse to keep on digging. Some climate scientists don't like this, because rather than fighting against climate change, they're now really fighting against the fossil fuel industry, and they've lost their original goal out of sight. You can see this in their reactions. According to The Guardian, Dr. Frederike Otto of Imperial College London, UK, said, "The science of climate change has been clear for decades. We need to stop burning fossil fuels." But science says nothing like that. And on Twitter, Al Jaber has been widely disparaged as a climate change denier. I find it hugely problematic that some very visible climate scientists mix up their opinion about what should be done with scientific facts. Don't get me wrong, I have no problem with scientists who have opinions. I have a problem with scientists who present their opinions as scientific facts and then call everyone who doesn't like their opinion a denier. According to those climate scientists, not only does this make me a denier, but also some of their own colleagues. For example, Miles Allen from the University of Oxford. Allen is the one who coined the phrase net zero and who invented extreme event attribution. He had the following to say about the reaction of his colleagues to Al Jaber. It's depressing to see the climate establishment reacting so furiously to a perfectly accurate statement by the COP28 president. To limit warming even close to 1.5 degrees, we must both scale down the use of fossil fuels and scale up safe and permanent carbon dioxide disposal. It's simply not true that to stop global warming, we have to stop using fossil fuels. What we have to do is stop dumping the carbon dioxide they generate into the atmosphere. Yes, fact is fossil fuels are the major cause of global warming. But fact is too that the problem isn't the companies digging up fossil fuels. It's not the fossil fuels, and it isn't even the burning of the fossil fuels, it's the carbon dioxide. The goal is decreasing the amount of carbon dioxide in the atmosphere. Let's not leave the goal out of sight, and let's not confuse facts with opinions. I also think we should appreciate the irony that climate activists are against fossil fuels unless their meetings are basically paid for by it. What is better, planting trees or covering the same area of land with solar panels? A group of geoscientists from Israel just looked at this and they say that solar panels come out way ahead. Trees breathe carbon dioxide, which makes planting trees a fairly obvious and technologically simple way to mitigate global warming. Trees and other vegetation take up about 2 billion tons of carbon dioxide annually, and they use it to grow. They create what's known as biomass. That's basically living stuff that stores carbon. Yes, you are biomass too. Most of that carbon is released when the trees or we die and rot away, but trees deposit part of the carbon into the soil where it can remain for a long time. Indeed, those dreaded fossil fuels are basically plants that have been dead and underground for a very, very long time. A fairly obvious way of decreasing carbon dioxide levels in the atmosphere is therefore to plant more trees. Problem is that planting trees competes with other land uses, such as planting crops that people would like to eat, or planting cows that they'd much rather eat. And in most fertile areas that people aren't currently using for food production, there are either trees already, or humans are busy chopping them down. This is why geoscientists say the best places to plant trees and other vegetation are semi-arid areas where there's some rainfall but not much. Basically, these are areas that aren't good enough for agriculture, but still many plants can grow there if one just plants them, and those could take up a lot of carbon dioxide. These areas that have potential for reforestation are huge parts of southern Africa and southern America, as well as Russia and eastern Australia, but also in some parts of Europe. According to estimates, the potential area is almost 1 billion hectares, or about the size of the entire United States. But here's the issue. Those areas that are prime candidates for reforestation are also good to put up solar panels, which raises the question, just which is better for the climate? So this group of researchers went and crunched the numbers. They compared a forest of solar panels and its potential for reducing global warming with an actual forest of trees. The question of which is better isn't just about how much carbon dioxide they remove or avoid. The question is also how much sunlight they absorb or reflect, quantified in the albedo. Both trees and solar panels absorb quite a lot of light compared to the dry ground, but just how much depends on the type of trees. The other main factor included in the study is the break-even time. That's how long it takes until a forest or solar installation fully offsets the warming created by its plantation or installation. Their analysis shows that installing solar cells took about 2.5 years to pay off the climate change created by their manufacturing, installation, processes and changes in surface reflection. Planting a forest, however, would take over 100 years of photosynthesis to offset the warming caused by its planting and reflectivity. They also found that installing fields of solar panels would be roughly 100 times more effective at mitigating carbon emissions than planting a real forest. Even in less arid climates, a forest of solar panels was over 20 times more effective at offsetting its own climate costs than a forest. So solar panels are better than trees. Science said it. Well, not quite. Indeed, the authors seem to be somewhat concerned that someone might take their results out of context. I wonder why. So they stress that they didn't look at forests in general, just at the reforestation potential in those semi-dry areas. So it's not like we should chop down the rainforest and put up solar panels there. The other issue is that they didn't look at the economic question. Because, generating energy with solar panels isn't of much use if there's no power lines going there. Trees have the advantage that you don't need to plug them in. A new study published in the journal Nature Geoscience discusses a hidden danger of climate change. That's methane, which is lurking in the deep oceans. And they say that it's more dangerous than we thought so far. Let's have a look. Methane is the main constituent of so-called natural gas, which is natural in the sense that it occurs in nature, like, literally everything else. Methane burns most excellently, and burning it produces energy plus carbon dioxide and water. So we usually think of methane as a source of carbon dioxide. But methane itself is also a greenhouse gas. Indeed, if it's released into the air, its warming potential is over 80 times that of carbon dioxide. This makes methane the second most important greenhouse gas on Earth after carbon dioxide. Though, actually, water vapor is an even more potent greenhouse gas than either methane or carbon dioxide. But human activity has basically no direct impact on the amount of water vapor in the atmosphere. That's because most of the surface of Earth is covered by water, and the amount of water vapor is then a matter of equilibrium between evaporation and condensation. Water vapor has an indirect impact on global warming, though, because warmer air can hold more water vapor. This means if carbon dioxide and methane cause some warming, then that warming will be amplified by the higher amount of water vapor in the air. So water vapor is a greenhouse gas that amplifies the effect of rising carbon dioxide levels, but we don't worry about it because we don't directly affect its amount in the air. At least not globally. Locally, we can affect the amount of water vapor in the air, for example, by irrigating large areas of land, and that can indeed locally change the climate, but that's another story. To come back to the methane, the production and transport of natural gas releases some methane into the atmosphere, which contributes to global warming. But the biggest fraction of methane currently comes from agriculture and livestock digestion, i.e. the infamous cow farts. There are also natural sources like wetlands and some smaller man-made sources such as landfills and wastewater treatment. Basically, what happens is that bacteria have a feast and they produce methane, and that gets into the air. There's a lot of methane frozen into the ground in the Arctic region. That's what's called permafrost. This permafrost is now getting warmer and weakening and starts to release methane. If all that stuff thaws, that'll much accelerate global warming. It's one of the dreaded tipping points of the climate system. And as if that wasn't yet bad enough, here comes this new paper. According to the study that just appeared in Nature Geoscience, there's another source of methane that might soon get released. That's marine methane hydrate, a solid form of methane which can form if the pressure is high enough. On Earth, it can be found deep underground in places where the edge of the continental crust meets the oceanic crust. The issue is that as the planet warms, the ocean warms and the ocean floor warms, and this pressure might no longer be sufficient to keep the stuff solid. So far, climate scientists considered the melting of methane hydrate to be of low risk because it's hidden under thick layers of sediment. However, the authors of the new study used three-dimensional seismic images to examine what happened with those methane pockets in a past warming period, about 2 million years ago. They found some instances in which the stuff migrated, vented into the ocean, and eventually into the atmosphere. But please don't get alarmed, because from a few instances of that happening in the distant past, it's difficult to tell how likely this is to happen again in the near future. The authors of the paper just somewhat vaguely say someone should think about it, which is probably a good idea. There's a silver lining in all this, which is that while methane is a very potent greenhouse gas, it doesn't stay in the atmosphere all that long. On average, it takes about 9 to 15 years for half of the atmospheric methane to be removed by natural causes. In case your head isn't already spinning, let me get it done now. The primary mechanism for methane removal is its reaction with hydroxyl radicals in the atmosphere. This process converts methane into water and carbon dioxide. The major source of these hydroxyl radicals is ultraviolet radiation impacting on the upper atmosphere. But here's the twist. Those hydroxyl radicals are also a byproduct of combustion engine emissions. So some researchers have said that reducing combustion engines might make the methane problem worse, though it's somewhat controversial how large this effect is. So trying to clean up one mess just creates another. Honestly, moving to Mars seems more appealing each day. Hello? Hi, Elon. No, I don't want to move to Mars. I was just, joking. Oh, they're not kicking it. They're looking for the pedal to open it. Every good trash can has one. Elon? Nuclear power is on a roll. In its latest success, Poland has authorized the construction of 24 small nuclear reactors at 6 sites across the country. And a good thing too, because electricity production in Poland is one of the most carbon-intensive in the world, with still almost 70% of the electricity coming from coal. Nuclear power is back in fashion in many countries because of its potential to decarbonize even energy-intensive industries quickly. The Japanese, who shut down their nuclear power plants after the Fukushima accident in 2011, are using them again, and they're planning to build new ones too. In California, environmentalists have stopped complaining about nuclear power and are now fighting to get the plants back online. In Sweden, teenagers demand that Greenpeace drops their resistance to nuclear power, and even the Germans are rethinking their decision to phase out nuclear power. It's a good idea if you're worried about climate change because nuclear power has very low carbon dioxide emissions. Not such a great idea if you're worried about your money because nuclear power has the reputation of being expensive and slow. This is why the small modular reactors are such a game changer. The idea of small modular reactors is that they're built in a factory and shipped to a location. Depending on how much power you need, you can connect several of them together. This has the potential to make the construction cheaper and faster. The reactors in Poland were approved earlier this month by the Polish Ministry of Climate and Environment. They'll all be built by GE Hitachi, a collaboration between US-based General Electric and Hitachi, a Japanese company. The reactor type is called BWRX-300. The BWR stands for boiling water reactor. These small reactors take 2 to 3 years to construct and can deliver up to 300 megawatts of power, which is enough to power approximately 2,400,000 homes. The small reactors run on enriched uranium and use a passive cooling technique which enhances safety features. In case of a loss of power, they can operate for up to 7 days without the need for intervention. Poland is not the only country going for this idea. Earlier this year, the government of Ontario and Canada authorized the construction of a small modular reactor of the same type and in the summer upgraded their plan to 4 in total. The elephant in the room is the cost of these small modular reactors. While the company says that the costs will be significantly lower both per energy capacity and electricity produced, then for conventional large reactors, it remains to be seen whether this works out as desired. The future is bright. No, not like this. This concludes our science news for this year. We'll all take a 2 weeks break and then resume in the second week of January. I'm not supposed to tell you, but I'll tell you anyway that we have a video coming up on Saturday that'll look at the cost and time problem of nuclear power in great detail. So if you found this video interesting, come back on Saturday. And the quiz for this week's science news is also up, so go and check how much you remember. See you on Saturday.